Well, good evening, everyone, and welcome to the first 60 Minutes in Space of 2013. I guess we're probably coming up on celebrating an anniversary. I think we've been doing 60 Minutes in Space for about 11 years now. So thanks for the support. I remember when we first started, we were in the little room off the cafeteria that holds maybe 25 people. And we counted ourselves with a capacity crowd if we had maybe a dozen. So it's really nice to see all of you here tonight. I'm Steve Lee, the chairman of the Space Sciences Department, and with me tonight will be Dr. Dimitri Klebe as well. And I always just sort of give the lay of the land here for any new folks. We just try to go through a handful of stories that have happened in the previous month or so and do it in a little bit more depth than you've probably been able to see in the news. And we each try to do things that are in our own areas of expertise. Dimitri's an astronomer, so he will take you to the far reaches of the universe, and I'm a planetary scientist, so I typically do things that are much closer to home, as well as human spaceflight and things like that. So that's the way we'll do it tonight, and we have plenty of time at the end for questions, but if there's something that's really burning when you see a slide, please try to get our attention and we'll address it while the slide is up. So I think without further ado, I'll turn it over to Dimitri.
All right, thanks, Steve. I'll stand over here in the light. So tonight I'm going to talk to you about actually a conference I went to at the beginning of this month, the American Astronomical Society meeting. It was actually the 221st meeting of the Astronomical Society. And I always enjoy going to these meetings because they have all these plenary talks that talk about a variety of topics, and I like to bring them back to 60 Minutes in Space and talk about some of the ones that I thought were pretty exciting. There happened to be 3 talks on exoplanets, or planets that are orbiting stars outside of our solar system, and I wanted to actually try to talk about all 3 of those talks. They had an hour for each one of them, so for me to do it in a half an hour, I'm not doing justice to the speakers. But they were the big theme at the meeting. And exoplanets, since we don't have David Grinspoon with us for a while here, I'm relegated to do that topic. So the first one I'll talk about was the one I'll spend most time on was given by Natalie Batalha, and she is a member of the Kepler team, and I'll give you a quick rundown on what the Kepler mission was. And she's just talking about new finds of these exoplanets. And then Heather Knudsen talked about atmospheres of some of these exoplanets and what we've been able to learn in that respect. It's amazing we can even see an atmosphere in a planet going around a star not other than our own. And then John Johnson talked about hot on the trail of warm planets around cool stars. And I'll let you know a little bit about that as well. So to get started here, I wanted to just give a quick primer. Most of the exoplanets that we had found early on were found by what's called the radial velocity technique. As a planet goes around a star, it tugs that star around as well. And so if you were to look at the star, you would see that sometimes it's coming toward you and sometimes it's moving away from you. And we can actually measure, looking at the spectrum of the star, we can see that the spectrum with the absorption lines that it has in it actually shift back and forth. And we are able to detect the presence of a planet that's going around it. And another bit of information that gives you is if you know what the star is involved, you know what its mass is, and therefore by the tug, you can actually get the mass of the planet that's going around. One thing you don't get, though, however, is you don't know what the inclination of that orbit might be. So the other technique, which adds to this as well, is what primarily the Kepler mission is working on, and that is looking at transits of planets going across their parent star. So basically you're looking at something like this. As the planet, if you happen to be in the right line of sight, you can see the planet actually move in front of the parent star. And what you measure is you watch that planet go in front, and you see that there's a dip in the brightness of the star itself. And the relative drop in brightness is an indication of the size of the planet. So the information that you get from this technique is that what the physical size of that planet is, as long as you know the properties of the star. You can also go back to these systems and measure the radial velocities of them and actually deduce the mass as well. But we don't have a lot of systems where we have information on both of those. Now, we were treated to our own eclipse in our own solar system earlier last year, if you remember, the transit of Venus. And so here's a Solar Dynamic Observatory video of it, and I don't know why it stopped mid-eclipse there, but I'll just move on there. But that was actually in ultraviolet wavelengths. So basically the Kepler mission is looking at that same phenomenon at stars at a decent, a few thousand light years across our galaxy. Now what it does is it's looking in a direction of Cygnus, and this little patch of little rectangles you see here represent the imaging sensors aboard the Kepler spacecraft. And they just stare in this exact same point in space all the time, and looking at almost 100,000 stars, looking for these transit events. And when they see those transit events, see those dips in brightness, they have an indication that there might be a planet there. But to verify that it's a planet, you have to see it go around its parent star again and see it dip in brightness. And then once again, you have to see 3 dips before you can confirm that there is indeed a transit there. Okay, in terms of the space that Kepler is looking at, this is just an artist's conception of the Milky Way here. Here's our sun. We're out here along the Orion spur, one of the spiral arms in the galaxy. And Kepler is kind of looking along a spiral arm. And so it's kind of sampling this volume of space in looking at those 100,000 stars. Okay, let's move on to Natalie's talk. And she had big announcements. These were kind of the major press announcements for the meeting and everything. And I'm going to show you a little video here in terms of how this field has evolved from 1995, from the first detection of the first exoplanet. And that was detected by this velocimetry technique here. And you'll see that there's some transiting things that weren't measured by Kepler that are also placed on this graph. And we're going to see an evolution in time up to 2009 and how many candidates we've actually detected. So that was the first one. By 2000, we had a couple dozen. And you can see most of them are radial velocity techniques. Now a few transits have then shown up here. And then in this next one, we'll go from 2009 to 2012, just looking at the non-Kepler type transits. So we've added to that. And then along comes Kepler, and boom, we have a lot of candidates. Now, I needed to just emphasize that these are just candidates. Most of them will never be confirmed, but we'll continue to go and confirm as many as possible. A lot of the discussions in these talks were about going through the statistics and figuring out, what percentage of these are actually going to be real. There are a few things that can have false positives, but the majority of these are indicating that there are planets. And I should also have pointed out how we're plotting things. Since the transit technique gives us the radius of the planet, and it's done in relationship to the Earth. So Earth is down along this line, and the period in days is how long it takes that planet to get around its parent star. So we're here at 365 days. So you can see that the majority of these samples are finding stars that are orbiting their parent planets at a much faster time scale than ours. And that's part of the technique. You remember, you have to see it go at least twice around. This mission's only been in existence since 2009. So as it continues to take data, and it is continuing to take data, it will start to stretch the bounds off into this direction. So what we really want are things really along the Earth line here. We want the smaller planets here. So just to show how the mission has been evolving, these are different things. After 13 months of Kepler data, they had 1,235 candidates. Then after 16 months, they had 2,321, and now they have, this is their last announcement, they had announced another 400 candidates, and you can see that the population of these is starting to push downwards on this graph. We're getting to smaller and smaller planets that we are actually detecting. So playing with this, the statistics of this a little bit, first of all, here's what they, detected up till now, and then this last go-around where they detected 400 more, the majority of them came in these small Earth bins here, so ones that are more Earth size here. So a 43% increase in the sample there. So the other thing that we're interested in now, we plotted things a little bit differently here, is now we looked at the relative radius, and instead of plotting it against their distance, we plotted against what we call the equilibrium temperature. In other words, what temperature would that planet be at if it was at that particular distance. And so what we're interested in is things that are here in this green band right here, where what should we call the habitable zone, where the temperatures are in an area which can support liquid water on the surface of those planets. So we really want things that are in the habitable zone, but are down here on the size of the Earth. So you can see there are not much that are populating that yet. So we don't have very good sample sizes there yet. Just to digress a little bit, there was an article that came out yesterday where they just discussing the habitable zone. It's not a totally trivial calculation to make, because you have to take into account the atmosphere of the planets and the fact that they, like our own Earth's atmosphere, will warm the planet over its natural equilibrium temperature that it would have if it was just a rock without any atmosphere at all. And what was interesting about this is that you can see Earth and Mars here. These are the size of the star that they're at. So the smaller, the cooler the star, the closer that habitable zone is to its parent star. But here we are at sun-like stars out here, and the Earth is really, in these new calculations, right on the edge of the habitable zone. They're a little bit closer, and it would not have been so good. So, but there's still a lot of work to be done in this particular area. Now, the other thing, let's see what else I was going to show on this. Oh, so I just went back to that habitable zone. So just focusing in on that one region right there. Here are the ones that are actually smaller, that are within the habitable zone, that are maybe candidates. So we can see that there's really none that are down here at the Earth-size radius. And just to select 4 of those, here are the kind of the most promising candidates here. And this one here is actually one that's orbiting around a sun-like star that is in the habitable zone. And I say that because it has temperatures that could support liquid water on their surface. Other thing that Kepler does is actually finding how many systems out there that have actually multiple planets. So here's the tally of that now, where there are several planets that have been found in where there are 2 planets orbiting, 3, 4, all the way up to 6 planets around there, though we only have 1 of those systems, and I'll just mention that a little bit later as well. So we're seeing multiple planet systems like our own. And here's where those actually plot the multiple planet systems. And the significance of this plot is we're again looking at the size versus its orbital radius here, is that these ones that are in colors, which represent multiple planet systems, they represent the same distribution as the ones that have single ones. A lot of times you can have a single planet, but with the transiting technique, you're not guaranteed to see all the transiting planets that are potentially in that system. So this does not mean that ones that Kepler has a single planet of doesn't mean that there's not multiple ones there. And the fact that this distribution is about the same between the two indicates that probably a lot more planets have multiple stars have multiple planet systems. Oops. Okay, so just looking at the probability of finding various small planets around them, this is kind of the graph that they have, but the statistics are not very good down on this end. We're looking at the number of planets per star that orbit at a 50 days. We haven't been able to extend that at a higher number of days because we just don't have the sample data for that. And you can see that as we go to a smaller radius here, planet radius, that we get more and more. So this is saying that there are more small planets around stars than there are large ones. The fact that it turns over here is more of a statistical thing. We do not think that turns over, that it goes up and up. So in other words, the predominance of planets are smaller ones. And this, is something that we wanted to confirm since the discovery of the first planet, which are these big, hot Jupiters. That was based on the technique we're using, but now we're using different techniques. We are indeed seeing more what we thought we would see, and that was the predominance of smaller planets. And so here's what we have to date in terms of the percentages. And now this is cranked up to 85 days there, and you can see that the percentages of planets out, or stars out there that have Earth-sized planets is on the order of 17%. Now, the question on how many of them are in the habitable zone, we don't have good enough statistics on that yet to say that. Now, when I talk about John Johnson's talk, he has something a little bit different to say about that, where he has actually made a prediction on that for at least these smaller stars. And I was just going to say something about the confirmation of these. Some of them are being confirmed by the radial velocity techniques. And the good thing about that, those are all the confirmed ones, but the velocity techniques, they also give you mass as well. So we want a lot bigger samples for ones that we have both the mass and the radius, because then you can figure out what the density of the stars and can figure out what its of its planet, and you can figure out the composition of it. Okay, and then there's ones which they have statistical validation as well. One of them is a pretty good candidate, which is the Kepler 22b, which has a period of close to 365 days. So this is, I think this is the record setter in terms of having one that is an Earth size that's close to where our Earth is. Now, I can't remember. I don't think that one is in the habitable zone, though. Just showing that they're pushing the envelope there. So, and then I'll talk about this a little bit more when I talk about John Johnson's one. These are the smallest exoplanets that we have discovered so far. So anyway, these are the highlights for there. I'm not going to read through them and everything, but basically there were these 461 candidates. It's looking like at least 70% of the stars that are out there have planets around them, and I'll speak to that a little bit more as well. Now, I'm not going to spend too much time on Heather's talk, but I wanted to give you a little bit of sense of how we actually can figure out what's going on in terms of atmospheres around other exoplanets. And what are some of the things that, and why do we even want to do it? Well, one of the things we can find out is how did a solar system evolve based on the chemistry that we can actually see within the planet itself. It also speaks to how the planets migrate around over time. One of the things we've learned about the discovery of the planets that we do know that they are not in the positions that they were ultimately formed in. And then ultimately we want to address the conditions of habitability. We may find an Earth-sized planet around another planet that's in the habitable zone, but until we actually assess its atmosphere, we don't know whether that is a place that could have life. And so I've showed you this one here where we're showing the amount of planets we're finding as a function of their size. There, for people who are doing atmospheres, the problem with the Kepler study here is that these ones shown in blue over here, the Kepler candidates, are really too faint for our techniques right now. We have to be out here with most of the planets being ones that have been discovered by radial velocities and such. And that actually limits it to the planets that are really, that are Jupiter-sized planets that we're seeing their atmospheres. Well, what's the technique that we use here? Well, we actually watch the planet go around the star, but instead of looking at the transit out in front of the star, diminishing the star's brightness, which we can look at as well, which gives us the radius, what we're more interested in is the secondary transit where the planet passes behind the star. And what you get from that, and I should say that these observations are being done by the Spitzer infrared space telescope. And so you get a transit as it goes behind there. And when you see both of them, you're getting the atmosphere, you're getting the emission from the atmosphere of the star itself, plus that of the planet. And when you watch the transit, you start off with you're looking at both the brightness of the star plus the planet, then the planet disappears and you just get the star. And by looking at the difference between those two, you can extract what the atmosphere is, or what the flux is from the planet itself. And you can do this at different wavelengths. And so this is the composition of the one exoplanet that has been most studied, and it has been studied from 1 to 20 microns, and everything that you see as a point here has been used with this transit technique where you've subtracted, the secondary transit from the where it's not in transit, and you get all these points. And then what you see in the black line is just a model atmosphere for that particular planet. So we're now able to measure spectrum via this technique of some of these other planets. And Heather went and talked about some of the things that we've been learning, but it was at a higher level than I really wanted to try to actually convey to you here. But looking at lots of these spectrum, and I hope you appreciate it. I'm not going to show you too many of those. But one technique that she did show that I thought was very interesting was actually getting at the third dimension, atmospheric circulation on some of these hot Jupiters. When you have these hot Jupiters, which are they're large Jupiter-sized planets that are orbiting very, very close to their parent star, they are tidally locked to their star, meaning the same face is always pointed toward the sun. So you can imagine that side gets pretty warm. But one thing, so this is the situation where if you were looking at that star at the hot side, it would look hotter and get cooler toward the edges and everything like that. But if you had lots of winds on that particular planet, it would actually start to go from this situation to one where it blurs it out, where if the winds were so high that it would actually make the temperature not so hot on that hot side. It's evening out the temperature around the planet itself. And so it turns out we can actually see that phenomenon by measuring this secondary eclipse thing. So here's imagine what we're viewing from our position here as it makes an eclipse. So when it has the primary transit here, this is when it makes a big dip in the brightness because the planet is going front of the star. What we are seeing, what phase of the planet are we seeing? We're seeing the back side of it. We are seeing the cooler side of it. Okay? When it's in its secondary eclipse, we see it on its hot side there. So if we didn't have any winds or anything like that, what we would see is the brightness of the planet do something like this here. If there are some winds, it would look like this. If there was lots of winds, like that third case where the temperature is all the same, you would just see this phenomenon right across here. And it turns out they've been able to measure this in some stars, and sure enough, they are seeing that there is actually, here's the 0, 0 point, you see that that peak or that trough there is not located there, it's somewhat displaced. So they are actually measuring wind circulations on some of these exoplanets via this technique. It just always amazes me how many different things they can extract from the transit technique. Okay, so anyway, there are things that are starting to emerge from these kind of studies, but the big problem right now is that we do not have any planets that are close enough that we can start looking at planets that might be a little bit more interesting to you and I, that are, say, closer to Earth-like via this technique. But we are starting to look to try to find if there are indeed more planets that are close by. Okay, the last talk I was going to talk about was John Johnson, and he gave kind of a very nice introduction about, why do we want to learn all this stuff? And so one of the exoplanetary science goals, one of them is understanding our origins. We as a solar system were, started off about 4.5 billion years ago, and as a molecular cloud that collapsed from some disk. Then planets formed within that disk. Then there was interaction between those planets. This is a whole migration history of the planets. And then what we really see today when we look at other planets is the ones that we detect are really on this current epoch. And in terms of observing, we really only get down to where we see some of these gravitational interactions. So looking at these exoplanets is we want to get back in to see how we as a solar system actually formed. We also are interested in the context of our solar system. We know of this until 1995. We only knew of one solar system, our own. We have our 8 planets. I know we used to have 9 here, but 8 planets. And how representative of this is of other planetary systems in our galaxy. Are we, very rare, or are we, just kind of run of the mill? And then probably the question that I think everyone has to answer is is there life that is out there on some of these other exoplanets? And this is a nice little quote from Jason Wright's thesis about, how these exoplanets are places, and they're not just things that are out there. So anyway, that's in addressing all of these things, origins, context, and life. We have these questions like, do planets exist? What can we say about this, a statistical ensemble of these things? And what are some of the detailed properties of that? And those are the things that we're trying to get at. In terms of what we've been able to check off, for things that are Jupiter-sized, we can check off all of these. Things that are Earth-sized, we know they exist now with things like the Kepler studies, but we do not have very good statistics on them, and we certainly don't have much in the way of getting any detailed properties of them. So John Johnson's main focus was actually looking at planetary systems around the smallest stars, the M dwarf type stars. And here I've show this graph again. We expect that actually to rise even higher than what the data suggests, just because of incompleteness in the data. But one interesting way to look at this thing is, now let's look at the size of the planet relative to the mass of the star that it orbits. And you will see that what is happening is that smaller and smaller, that you're seeing smaller planets around smaller stars. So perhaps these M dwarfs are the place to really look for habitable planets and stuff. So just on the list of stars, here's our sun. It's a G star. 70% of the stars are actually these red dwarf stars. So there are a lot more of these M dwarf stars. We're not that common of a star. And the fact that there is more planets around, small planets around these stars, actually make these the more commonplace place to find habitable planets. And So here is just kind of a fun little, not animation, but artist conception here of all of the confirmed planets and their stars that Kepler has found. So here is actually, just for scale, is our own sun size with that's Jupiter, and you would not be able to see Earth on that little thing. It's a very, very small dot. So John Johnson and his team are basically looking at these guys that are down here. So they still don't have much of a sample as well, but even though that would be a better place to look. And one of the things that's good to look for that this is a good place to look is that these smaller stars have the planet is a bigger fraction of the size of the star. So when it comes into transit, it produces a bigger transit. So there's an easier signal to actually see than the smaller signals that you see from, say, a sun-like star. The other thing in terms of looking at where their habitable zone exists, here to scale is what a sun-like star's habitable zone looks like. So this is going from, well, you saw that other one from Earth to Mars, basically. And here is that of an M dwarf. It's a much smaller star. It's much tighter in there, but that also means that things are moving around more quickly and things that actually can be detected by Kepler itself. One of the problems with the red dwarfs, though, is we don't know a great deal about those stars. So you only know the planet as well as you know the stars. So if you do not know the size of that star very well, then you don't know the size of the planet. And a good example was actually this one that John Johnson talked about was Kepler 42, which actually harbors the 3 smallest known exoplanets. And here they are on a nice little graph here. They're these 3. Unfortunately, they are not in the habitable zone, but they are actually smaller than Earth. This smallest one is just a little bit bigger than Mars. When they were first found, they were thought to be a lot bigger, and that was because they did not have the right size of the star. And then they figured out that the star was an identical twin to a star called Barnard's star, and they were able to really figure out what its properties are, because Barnard's star was close enough that we actually measure its physical size. So that placed that as the smallest planets that we had. And then and then there's the Kepler 32 system that I said I would touch back on again. This is the one that has this one has 5 planets in it, and it's actually orbiting around one of these red dwarf systems here, and it's telling them a lot about the frequencies of these kind of systems. And if you look at how they are distributed and everything, those are those 5 planets in here. Again, we've got now mass and radius. We're able to actually get mass from these ones from another technique I can't get into, but they represent the same distribution of other things that are found in Kepler. So the belief is that there are lots of these planets or multiple planet systems orbiting these red dwarf systems. And I don't know why it went black. Oh, okay. Yeah, that's right. So John Johnson and his team also did a bunch of statistics and making predictions as to how many of these star systems are out there. And I just love this one. They're kind of like cockroaches. And we only see a fraction of the amount of transit. So if you find one, there are really a lot more that are out there. So looking at the statistics there, he had this paper that came out on the, I think it came out on the 31st of December. So this was big news, and a whole bunch of news places came out there. But their thing is that there's 1 planet per planet, plus or minus 0.1 there. And so a lot of news stories got a hold of that. So you might have seen this thing, 100 billion alien planets fill our galaxy, because we got 100 billion stars that are out there. So they picked up on that. And then interestingly, this is his summary slide and everything, is that he actually does make a prediction that there are Earth-sized planets in the habitable zone of these ones, at about a 6% rate. So, so he has made a prediction about things that happen at least for this size of a star. So it's not Earth 2.0 yet. Earth 2.0 is going to be something that's going at 365 days around, or comparable to that is of the Earth's size and everything. And another thing in terms of doing the statistics is important is that these Earth-sized planets, there's a 95% confidence that there's one transiting an Earth-sized planet in the habitable zone within 31 parsecs, which is about 100 light years. That's our solar neighborhood. So that means that we can do transit studies of these nearby stars and hope to find at least one of them. And I'll just finish with this last slide, which is actually the conclusion slide from Heather's talk, which I just think is interesting. We're now up over 3,000 candidates of planets now, from one at 1995. But if you look at what we've really sampled, this is our sample space. This is the artist's conception looking on top of the galaxy. I told you Kepler is looking off in this direction right here. That's Kepler's little cone of observation, and then we've kind of sampled our solar neighborhood, but not nearly to the degree that we can actually do so. But this is exciting stuff. I'm hoping in my lifetime that we see us find some habitable planets. And there are a few things, if we ever measured atmospheres and stuff, that are telltale signs of finding life on other planets. All right, I'm done with my portion. I'll turn it over to Steve. Thank you.
All righty, so let's come closer to home. I've been doing this, I can't believe it, for 9 years now, updating the Spirit and Opportunity missions. And this really is a big anniversary. Opportunity landed just 9 years ago last week, and it was intended to be a 90-day mission. So today we're on day 3,207 Martian days, a solar day, and that's 36 times the expected design life of this mission, and it's still going strong. So I'll just give you a brief update on what it's been doing for the last few months, just to refresh everyone's memory of where Opportunity is. It landed up here inside a small crater about the size of this planetarium dome. And for the last 9 years, it's been driving across this flat as a pancake plain. And it's now perched on the edge of this 22-kilometer diameter, very old, degraded impact crater called Endeavour. And it's been sitting here at this feature called Cape York on the rim of the crater for it's at least 6 months now. And this is a view from orbit of what Cape York looks like. So the crater itself is off to the right here. This is sort of a hill. It's just maybe at the highest point, it's 10 meters or so tall. So Opportunity, driving across the plains, came up here. It drove around most of Cape York. And for the last 4 months or so, it's been going across this area called Matejevic Hill. This is named in honor of a scientist who worked on all of the Mars rover missions, starting with Pathfinder, and he passed away right around the time that Curiosity landed this last year. But from orbit, this area has a very distinct signature of clay minerals. And what is real exciting to geologists about clays is they form in the presence of standing water, typically. And so that would indicate that the minerals, the rocks we find here, could well have been laid down underwater, and that's one of the things that they've really been looking for. And so they drove around Matejevic Hill, and right now they're sort of circling around in this area right here because they think they've actually seen a likely deposit of these clay minerals, and so they're zeroing in now to start doing the chemical analysis on those. This is just a little bit closer view, and this is a mosaic of Matejevic Hill. This area right here is most of the hill that was assembled right between about Thanksgiving and the middle of December. And so this is just the view that Opportunity has. And what I want to do is move in a little closer to this area. And sort of this rotten looking stuff here, but what's really interesting is these flat deposits. I'll show you another slide. I think it's probably the next one. Yes, this is a false color view, enhancing the colors, and you see what looks like sort of an eroded rind on top of the rock. And so this is the underlying stuff. There's something, another layer that was covering that, and that's being eroded away. And this would be, if this was on Earth, this would be very characteristic of rocks that are predominantly made out of clay. And so they're in the process now of moving in on one of these flat rocks to actually deploy their the alpha particle X-ray spectrometer on board to determine the composition of that rock. And this is a view of where they're sitting right now. This was the last images returned just a couple of days ago. So that's where Opportunity is perched right now. And here it is deploying its arm to begin this sampling activity. So hopefully within another month or so, we'll be able to report back on have they actually found the holy grail they've been looking for, which are these clay rocks. So this is the sort of the recap of the mission. Again, we're 3,207 days into the 90-day mission of Opportunity. It's driven a little over 35, almost 35 and a half kilometers. Again, originally they had hoped that it would drive at least 600 meters, so 0.6 kilometers. And they'd hoped for a few thousand images back, and we just, we're rapidly approaching 200,000 images from it. So stay tuned, and we've been updating this ever since early 2004, and I expect we'll be doing it for quite a while longer. And by the way, I was thinking when I was sitting in the back of the room, I'd said about approaching our 11th anniversary. I think I'm wrong. I believe 60 Minutes was originated back in sometime in the year 2000 by Laura Danley, my predecessor here. So we're actually closer to 13th anniversary. Okay, so now let's move to the other star on the surface of Mars, and that's the Curiosity rover. Curiosity, if you remember, landed on August 5th of last year, and today we're up to day 173. And they still haven't gone all that far. They're less than about a kilometer, but they've mostly been learning how to use the spacecraft, and they've been verifying that all of the instruments are working, and they've sort of been going through the checklist to make sure that everything's up to snuff before they actually head off to the mountain that's in the middle of Gale Crater, which is their real target of this 5.5 kilometer high mound of sedimentary rocks in the center of the crater. But I expect they'll be leaving this area within another maybe 1 to 2 months, and then starting the drive, which will probably take them more or less until the end of this year to get to their real hunting ground for where the mission really wants to be. But I'm going to back up a second. Just some really cool images that have come in recently, and I want to take us back to the beginning of Curiosity and show you what the origin of what you'll see in a minute was. So this was when it was launched. leaving the Earth. So here's Curiosity itself. This is where the rover was. This is the heat shield and the entry capsule for the atmosphere. And the back part of the spacecraft, which we'll see closer here, this is called the cruise stage. It had propulsion, solar panels, provided power and stability. So it got the spacecraft to Mars. About 10 minutes before landing, the cruise stage separated. And you'll see that right here. And so there's the entry shell, there's the cruise stage. And before it hit the atmosphere, there were two 75-kilogram weights that were dropped off. That's about 150-ish pounds. And that changed the balance point, if you will, of the spacecraft. And so that was the way that they were able to aim it in the atmosphere, by having the heat shield appropriately oriented so that it would sort of steer its way through the atmosphere. So the assumption was that those tungsten weights that dropped off, they'd probably reach the surface, but they're not all that big, so it'd be sort of a needle in a haystack effort to actually find the impact sites for them. But the cruise stage itself, it was assumed, would burn up in the atmosphere. It was going about 12,000 miles an hour when it hit the atmosphere. They didn't believe it would actually survive to the surface. But lo and behold, last month, the super spy camera on board Mars Reconnaissance Orbiter, which can see things, it's got a resolution of about 25 centimeters per pixel, so roughly a foot per pixel, and it saw some interesting things on the surface, and I've got squares around them. There's this dark stain here, couple here, and another one over here. And so let's look at these at full resolution. This, it's believed, is the cruise stage where it impacted the surface. This is about 50 kilometers west of where the spacecraft itself landed, and that would be consistent with where they think these things would come down. And there's also this big splash of material, and that could be the onboard fuel and things like that got sprayed across the surface. And there's a crater that's maybe 3 or 4 meters across right in the center. So that was sort of a surprise. This is, on that first picture I did, this was the one that was off to the right. It's thought that this is another piece of the cruise stage. And so it probably did break up into at least 2 chunks coming into the atmosphere. And then these, they believe, are the 2 tungsten weights, because they would come down fairly close together. So that was a big surprise, and that tells them something about the Martian atmosphere, about how how you might get things through to the surface. And so it's a good engineering experiment, if nothing else. But just the fact that they were able to find these things is sort of a big stroke of luck. Okay, so let's talk about what they've been up to for the last couple months on Curiosity. So this was the landing site, and this dark stain here is where the dust was disturbed by the landing itself. And so as quick as they could, they drove out of that area so that they would be out of the contaminated zone. And they've been slowly working their way across to this area, which was called Glen Ellig. And what they wanted to do, just from orbit, this is a really interesting site, because you can see there's one type of terrain right here. There's sort of another type just visually right here, and then there's a third type right here. And so right in this area, you've got a junction of these 3 different surface types. And so they really wanted to get over to this area so that as long as they were going to spend some time exercising all the instruments just to make sure they were working properly, you might as well get into an interesting area and look at something that might give us some really good science in the process of testing things. And so they've actually been in this area for about 2 months now, and sort of circling around, looking at the deposits. And it's a fairly exciting place to be. I've got some scale bars here to show you how big things are, but they're seeing lots of rocks that have these layers in them, and the layers come in at different angles, and geologists call that cross-bedding, and that's a really good indication that this site was in a stream bed, or at least it had water flowing across it. And these rocks would be the remnants of where you've got small dunes drifting across the bottom of the stream. And the way that the dunes migrate is they go along, and then the front edge sort of drops off, and that marches across the surface. So when it gets dried out and cemented into a rock, you get these layers that are coming in at all these different angles. So that's one good indication we have that this area was in contact with flowing water, which is what they'd hoped to find. And then this is the area that they're actually sitting in right now, where you see this texture on the surface, and boy, it looks a lot like what you'd expect to find on the Earth, where there'd been standing water, and it dries up, and it sort of leaves mud and rocks behind that sort of dry up and make this sort of scalloped texture. And so that's another good indication that there was lots of water here in the past. And then this rock, you see these little black spots, these sort of zits on the surface of the rock. And those are what we think are concretions. And these are, we've been seeing those a lot at the Opportunity site, where there's an existing rock, groundwater percolates up through the rock, and if the groundwater has dissolved minerals in it, as it goes through this saturated rock, those minerals can precipitate out and form little spherical particles, the size of maybe half a BB up to a centimeter or so across. And so we're seeing lots of those, and it's also sort of this crusty layered rock. And again, all of that is consistent with water being in this area. So just to remind you for a second of all the different instruments that are on board the rover, and I'm not going to go into all of these, but it's got 18 different cameras. It's got a radiation detector to look at the background and cosmic radiation. It's got a couple of chemistry experiments to determine the mineralogy and any organic chemistry that's in the soils. It's got a descent camera, and then it's got this on the end of the arm. This is an alpha particle X-ray spectrometer, which again gives you the chemistry of the rocks, and it's got a microscope camera. And then this is what I'm going to spend a little bit of time talking about. It's got a drill and a little scoop and a wire brush, and those are the parts that actually interact with the surface to help you collect samples of the rocks and the surface. And all of these other instruments they've been testing throughout the drive. This suite of instruments are the last ones to be tested, partly because they're the hardest to actually use. It requires a lot of dexterity to move the arm, rotate the turret to just the right orientation, put it down on the surface, and interact with it. So they've been slowly gearing up for what's about to happen. And this is just a close-up again of what the end of the arm looks like. This is it's sort of a garbage can lid-sized device on the end of the robot arm. And so here's something we'll talk about, the dust removal tool. It's a wire brush to brush dust off the surface, and then the drill itself. And let's just move on. So the first thing around Thanksgiving or so, they did their first scoop with this little sort of tablespoon-sized scoop on the end of the arm that can pick up fine material like dirt, essentially. And that has all worked exceedingly well. And this is
Hello, I am
a
Justin
view
Lin
of the
lead
first
gallery
use of the
for MER
brush.
Science Laboratory mission, and this is your Curiosity rover report. Over the winter holidays, Curiosity was parked at a location dubbed Grandma's House at Yellowknife Bay. At this location, Curiosity took a series of images to create panoramas of the surrounding area. In addition, the team downloaded as much data as possible from Curiosity to free up the onboard data storage space to give her a fresh start to the new year. Once the new year approached, Curiosity was ready to spin her wheels and stretch her arm. She started off with a 3-meter drive to an interesting feature called Snake River. Over time, dust has accumulated on all the rocks, and it hides features such as fissures, inclusions, or pits that are of interest. At this location, the team selected a rock for the first time use of the dust removal tool. The tool has a set of spinning metallic brushes, and this allows for the features to be exposed for unobstructed APXS or ChemCam observations. While these activities are taking place, the team is searching for a suitable rock to test out the rotary percussive drill. This is a very exciting activity because it will be the first time that we will be drilling into a rock, acquire a sample from deep within the rock, and also sort and transport it to the science instruments on board Curiosity. This has been your Curiosity rover report. Please check back for more updates.
Okay, so that gives you the gist of what they did the first part of this month. And this is just a better view of that first brushing of the surface, and that has worked quite well. And this is a microscope view where they just, what we're looking at in this second picture is, I think, roughly an area like I just outlined there. And so that's one of the reasons why you would brush it off. You want to use the microscope. You don't want to just see dust, although there's still some dust left, all these little particles, but you do want to be able to see through to the surface to look at the textures and things like that. And another thing they've done, the microscope camera, for the first time, we have a camera that can actually take pictures at night on Mars. And this is one of their first images. This was done just within the last week. And so it's after dark, middle of the night. They put the camera down near something. They have LED lights that come on to illuminate it. And so this is actually a calibration target on the rover itself. There's a penny right here, so that gives you an idea of the scale. And not only can this work in white light, so visible views, but it also has ultraviolet lamps. And the idea there is, for any of you that have been in our gem and mineral hall, you know that a lot of minerals under ultraviolet, they fluoresce different colors. And so this, again, is another diagnostic tool we can use of look at rocks at night. If we see characteristic colors on the rocks, that might tell us a lot about the rock. And so I think it's going to end up being one of these two spots. This is a fluorescent paint on the calibration targets. There we go. And so this is using the UV lamps, and this is just a reflection of the LED bulb. But there's the, if that was a rock, we'd be very happy to see that. And so this was the first view of an actual rock on the surface. This was an area where they drove up with the wheel and sort of scuffed it. That's what this white spot is. They've scuffed through all the dust. And so this is the visible view. And here's the ultraviolet view. And you might get all excited about this, but in fact, the people analyzing it say, well, that's just because it's such a bright surface that it was scuffed up. And so they're not interpreting any of this as actually being fluorescence. But it does show that the system works, and I'm rest assured they're going to be exercising this quite a bit in the future. So this is the drill system itself, and this will be the first time we've been able to actually drill into rocks on Mars, other than just a grinding wheel that grinds through the surface. But this is it's a hammer drill, and so it's the type of thing you might get at, Home Depot if you're wanting to drill holes through your concrete foundation or through a sidewalk. So it hammers back and forth at the same time that it rotates, and it powders the rock that's directly in front of it. And then by spinning, it's got sort of an auger here, and it draws the powder up internally and can sort it out and then dump it into one of these chemistry experiments on board the rover itself. And so this is the final piece that remains to be tested now. They have yet to drill, but they have selected the location that they want to look at. And in driving around this area that I showed you a little earlier, one of the things they're seeing are these bright veins crisscrossing the rocks. And they've actually shot these with the ChemCam, the onboard laser system that lets them determine the chemistry from afar. And it looks like it's calcium sulfate, which would be gypsum on the Earth. And that, the interpretation is that these rocks were fractured and water flowed through the rocks, and then the calcium sulfate precipitated out of the water and filled in the veins. This is an example of what this would look like on the Earth if you had gypsum in cracks on a rock. And so what they've decided to do is go up, and this is going to be their first target, is in one of these veins to actually drill into what might be gypsum, pull it into the analysis tools on board, and really confirm that that's what it is. And this was the view from the chemistry camera. So right here is where they zapped the rock with a laser, and they did detect high concentrations of both sulfur and calcium. And so that's all consistent, but the proof will be in the pudding once they drill into the rock. And so here's another video of how they've
Hello, I'm Justin
found
Mackey,
these.
and I am the engineering camera team lead on the Mars Science Laboratory mission and a member of the MSL Science camera team, and this is your Curiosity rover report. The rover has been investigating the Yellowknife Bay area as part of an effort to pick the exact location of our first drill activity on Mars. The images being returned by Curiosity show a diverse collection of interesting features, including sedimentary rocks, pebbles, cracks, nodules, and veins. The vein features are seen as a bright white material, and we see them just about everywhere we look in Yellowknife Bay. The ChemCam instrument has found that these veins contain elevated levels of calcium sulfate, likely in the form of basanite or gypsum. Gypsum veins are also seen here on Earth and are associated with water percolating through cracks in fractured rocks. The exciting news from all of this analysis is a candidate site where Curiosity will conduct its first drilling activity. This site is located only a few meters away from the rover's current location and lies in a flat area suitable for drilling. The team hopes to drill directly into one of the veins, place the powder into the SAM and Chemin analytical instruments. These instruments will give us detailed information about the composition of the material. We'll be driving over there in the next few days. On our way over to the drill site, we're planning on using the rover's wheels to crush some of the nearby veins and examine the freshly broken material. This image from Sol 135 shows an example of how the rover can break open soft rocks with its wheels, revealing the freshly exposed material. I'm Justin Mackey, and this has been your Curiosity rover report.
Okay, so this was an image taken just, I think, a couple days ago. Here's a tire track, and you can see that they're in the process of doing this. This rock is sort of crushed and broken open, so that's, it's nice to have a one-ton rover that, you know, you're not just sort of skittering across the surface. You actually have enough mass that you can break things on Mars. So this was taken, I think, a day ago, and this is just the view of the drill itself. And so there's the drill bit sticking out and getting ready to put on the surface, and here's they're exercising and trying to practice placing it on this deposit in preparation for drilling. And so the latest word is probably within a week is when they expect to do this first drilling activity. So perhaps by this weekend, but more likely early next week. And so again, stay tuned, and I'll have a report on that probably next month. And this is just filed under scenery. This is looking where they're parked right now, and this is the far rim of the crater. This is probably about 20 kilometers away, but pretty cool vantage point for the rover. And so here's the recap on Curiosity. It's day 173. They've driven a little less than 3/4 of a kilometer, and so far they've returned a little over 40,000 separate images. But so far, everything is working just perfectly, and it's only going to get better. So stay tuned. Okay, so quickly I want to move to the human spaceflight program, and we'll go into this in a lot more detail at some point in the future. But everyone knows that the last shuttle mission flew in July of 2011, and we've been working on what's going to replace the space shuttle as far as being able to have American astronauts launched on American spacecraft again. And so this is the Orion spacecraft. This is built by Lockheed Martin, which of course is here in Denver. But one of the items that had yet to be determined was the service module part of this, the power system, the propulsion system, the life support, all the oxygen and water and things like that. And just in the last 10 days or so, NASA has announced they've signed a cooperative agreement with the European Space Agency, and ESA is going to provide the service module. And so that's actually a major step forward. First of all, it gets us the engineering now can move forward. But second of all, it means that in these deeper space missions, like sending crews back to the moon or to asteroids or eventually on to Mars, that this will be an international effort. And the thinking is that by dint of the several $billion it's going to cost the European Space Agency to develop this and deploy it, that they will be given space on board some of these early missions with European astronauts, the same as sort of this bartering system that's done on the space station. So that's been decided, and the first test flight of the Orion capsule without the service module is expected to be done in late 2014, and that will be just an Earth orbit flight, but it will test getting it into orbit and then diving it back into the atmosphere and popping the parachutes and recovering it. The next mission is expected to be in 2017, and that will be with the new rocket called the Space Launch System that NASA's developing, and that will actually go around the moon and slingshot back to the Earth to test everything from a deeper space perspective. And so this next slide is going to be an animation of how they are proposing that mission will proceed. And so here's the SLS. This is actually larger than the old Saturn V's that launched the Apollo missions to the moon. It's got 2 solid rocket boosters derived from the space shuttle use, and then it's got 4 space shuttle main engines in the core stage. And so there's Orion and its service module on an upper second stage booster to send it on its way to the moon. It pops 4 solar panels. By the way, the service module is derived from the automated transfer vehicle, which the Europeans have been flying as a cargo carrier to the space station. So they've already got a lot of experience on building that sort of thing. And this first mission will be unmanned. It's still in the testing phase. And it will just slingshot around the moon and then head back to the Earth. So that's what they hope to do. And I still find it relatively amazing at how slow this is going to happen. But if this test flight happens in 2017, the next mission with a crew on board, which will essentially do a very similar mission, will be in 2021. So I want to end up with just a quick report on what's going on the International Space Station. So when we last talked, a new crew had launched, and the existing 3 people on board were ready to come home. On December 18th, another 3 crew members were launched from Russia, and they arrived just before Christmas. And so here's the total crew that's on board now. These were the folks that were launched back in October. These were the folks that launched in December. And I'll come back and say a few words about them in a second. And so this was the nighttime launch of the Soyuz rocket with the 3 new crew members. And they got there just in time to celebrate Christmas on board the space station. So that was just a nice present for the guys on board to have some company for Christmas dinner. And the final thing, and this was just announced in the last week, is that NASA has contracted with a firm called Bigelow Aerospace, and they specialize in inflatable structures for use in space. And this was something that was proposed back in the 1990s to make some of the modules on the space station of these inflatable structures, but then budget cuts led to that being canceled. This company has gone on and done a couple of test launches on their own, put these things in orbit. They've worked just fine. So NASA has contracted with them to do a test of one of these structures on the space station in 2015. And this is an animation of how this will work. So the module itself will be launched on a Dragon capsule, the SpaceX cargo carrier. And this is going to be a fairly tiny example. I think it's something like 20 feet long and about 12 feet in diameter or so, once it's inflated. And so they'll pull it out of the cargo carrier, dock it to an existing module on the space station, and then it inflates. And this is not going to be a real operational module. It's got a hatch on separating it from the space station, but periodically over about a 1.5 year period or so, it will be opened up. The crew will go in and check it out, and they'll probably stow some things in there, just use it as storage. But it's really meant to be sort of an engineering test bed where they have it highly instrumented with all sorts of temperature gauges, pressure gauges. They want to make sure that the space environment, like micrometeorites, don't puncture it. And so it's just a good way to test it before they actually commit to having things like this with crews on board. So that's at least a step forward as far as advancing the engineering for future missions. Okay, so that's really where I wanted to end, but I just wanted to plug a program that's going to be on February 19th. I'd mentioned those first 3 crew members. Back in mid-October, I was actually lucky enough to go to Russia and see this launch of the crew. We were there for 10 days, looked at the training facilities for the cosmonauts and the astronauts, got out to look at how they assemble the rockets, and then got to see the launch. And so I'll be doing an hour-long program in Ricketson Auditorium. It's partly a travel log showing you all the amazing things that we got to see, but I also wanted to go into some details about just how does the Russian space program work. We're actually using them now, where they've been very close partners throughout the era of the space station, starting in the late 1990s. Currently, this rocket and the Soyuz spacecraft, this is the only way we have to get astronauts into orbit. There's no other spacecraft that can fly humans on board. And so I want to go into some depth on how that all actually works. So I'd invite you to attend that. You can check our website, and there's also our online reservation system. So February 19th. And our next 60 Minutes in Space will be a week or so after that, February 27th. And I think you all found your way here tonight, so I don't need to tell you how to get in the door. But I think we'll stop for tonight, and we'll open it up to questions. But thanks, everyone, for being here. And we are running late, so we'll give folks, if you'd like to step out at this point, go ahead. Thanks. I'm sorry?
Isn't there a date change in February?
That's okay. I looked on our website right before we came in, because I've done this before. I'll give you the wrong date. Okay, thank you. Okay, questions? I can't see any hands. Okay, right here.
How close is Dragon to getting their craft man-rated transport crew?
So how the SpaceX, the Dragon capsule, it's being developed into a possible commercial crew vehicle. And the question is, how close are they? On paper, they claim they'll be able to do a test flight in 2015. And I think we'll do a dedicated 60 minutes either next month or the month after that of these commercial crew proposals, because there's actually 3 different companies developing this, so probably only one of them is going to be chosen. So there's SpaceX with modifying the Dragon. Boeing has a capsule that looks a lot like the Orion. It's sort of an Apollo-esque capsule. And then a local company here, Sierra Nevada, is developing a space plane called Dream Chaser. And there's news, I think it was just yesterday, came out that they expect to do their first drop test of the Dream Chaser at Dryden, Edwards Air Force Base, essentially in California, where they'll carry it up 15 or 20,000 feet, drop it, and let it glide into a landing as their first actual flight test of that. And that's likely to happen within the next 6 weeks or so. They think the spacecraft, or the Dream Chaser prototype, will be leaving Colorado within about 2 to 3 weeks. And then a few weeks after that, they expect to do that test. So there's lots of things happening right now. Boeing claims that they can do a test launch around the 2015 timeframe. Sierra Nevada says 2016-ish for a first test. We'll see. A lot of this depends on the NASA budget, how Congress deals with them, because it costs a lot of money to develop these things from scratch. So, but I think we do need to get everybody up to date on this, because this really is happening now, and I want everybody to be familiar with that. Okay.
Yes, I was wondering, do double stars either increase or decrease the habitable zone with planets?
So the question is, like, how do double stars affect the habitable zone there? So when you have a double star, a lot of times the separation is huge, so you can support a habitable zone set of planets around a particular star. Obviously, if the stars are really close binary in the system, that's a trickier situation. But in a lot of the double star systems, their separations are like, if we were in a double star system, yeah, it would be cool to have another star in the sky, but it wouldn't be that bright that would affect the radiation balance on our planet. So it wouldn't affect the habitable zone.
The lack of Jupiter-sized planets in some of these discoveries, can they explain why?
The lack of Jupiter planets. I don't know that they sense that there's a lack of Jupiter planets in these discoveries. They're now getting more toward. I mean, the whole thing with Kepler was a census of how many stars out there have planets and what are their size distributions and everything. The first Jupiter-sized planets that we actually found were like, even larger than Jupiter. But the odd thing was that they were orbiting so closely to their parent stars, and so that was strange. But it turns out that was just really the technique that we were utilizing to get that. So. In terms of our own solar, are you thinking like in comparison to our own solar system and everything? And we've got 4 rocky planets compared to, well, several of the other Jovian type planets or the gas giants and such. But our system is looking, I forgot to point that out in the last slide of John Johnson. Our system is looking more rare. One sense it's rare is because most of the planets are going to be found around these lower mass stars. But the other thing is just whole dynamic of where our Jupiter is in a solar system. It seems to be a little bit different than that found in other systems as well. So, but I don't know that we sense that there's a lack of them that are out there.
In the back.
Maybe. Yeah.
You.
Our dwarf stars, they're more stable, aren't they? So they could be pretty old and temperature fairly consistent over long periods of time.
Yeah, the question is like the stability of the dwarf stars. So the more massive a star is, the shorter time it actually lives. So our sun, a G-type star, lives 10 billion years. We're halfway through its lifetime. AM dwarfs live like 100 billion to 1 trillion years. So no M star that has ever been formed in our universe since the Big Bang has ever died. The thing is about stability, though, is that they may be susceptible to more flaring activity. We don't know that much about them since they're so faint and everything. And because of that, you got planets that are orbiting so close to their parent star that they can get roasted with flares, whereas we're a little bit safer. So one of the things about our star is it is a more, it has activity, but it's not as crazy as some of the other phenomena we've seen.
Interpretation was is that maybe some of those planets could be 2 or almost 3 times as old as you.
Yeah, that's true. But we think that a lot of in terms of age of planetary systems and things, our planets, the rocky planets, are made out of materials that had been synthesized in supernova explosions. So when did those first generation of kind of Earth-like planets start to exist? I didn't get into it, but stars get more and more metal rich as time evolves. So, we formed 5 billion years ago. The universe is 14 billion years old. So there certainly are some that are older.
When you say slingshot around the moon, how close to the moon is
Gosh, off the top of my head, I don't know. Within probably 100 miles or so. Yeah, it's not really critical. They're not going into orbit, but they need to obviously miss it. So, but it's more just to use the gravity. What the real utility of doing that is it gives you when you come back to Earth, it gives you the velocity that you would have coming from a lunar mission or from deep space. And so it gives them a much higher entry velocity, which is, of course, what they need to be able to survive, since it's not really intended to be just a low Earth orbit spacecraft. So that's the purpose of that one.
Is that why we saw it with multiple parachute systems?
Well, the parachutes, it's a very heavy spacecraft, even though it doesn't look anywhere like it's all that big. But yeah, the different phases of that, I think the first one that you see, it's called a drogue chute that just stabilizes it, and then that pulls out the second set of chutes, which slow it a little bit, but those are then used to pull out the main chutes, the 3 big ones you saw right at the end. And each step is essential because you need the first one to get the second one out and the second one to get the main chutes out. And I think they are specifying it that on that last phase, if one of those 3 chutes fails, it could still be a survivable landing. So you need 2 of them, though. So and they've been doing tests on that, just dumping this out of airplanes for the last couple of years. So they've got quite a few parachute landings under their belt at this point. But the real big thing is coming into the atmosphere instead of what you do coming out of Earth orbit at, say, 17,500 miles an hour. You're talking 25 to 30,000 miles an hour if you're returning from deep space. So the heat shield has to be able to survive that. Okay.
Quick question on Ryan. I think about with deeper space missions, are they talking about adding a crew compartment onto the end of that? We take it off and just.
So the question is, if they do a deep space mission like an asteroid is probably the deepest space initially, they're not going to just live in this capsule for 4 months or 6 months, whatever. So yes, I think the talk is do something like a module from the space station, something of that size that would have all the food and the life support and room for the crews. And but that has yet to be developed. They really have not, other than these 2 test flights, 3 test flights, the one in 2014, 2017, and then the first manned mission. Those are the only ones that are really well-defined at this point. And then what they're going to use it for after that, it's all just concepts at this point. I think in the last week or so, I saw an article that Boeing has proposed sort of an infrastructure for using this type of system to get people to Mars. And it involves a lot of separate modules that get landed separately and or put into Mars orbit or whatever well before the crews get there. But that's for a future 60 minutes. We can talk about that.
And this module would be launched separately as well. So, I mean, it wouldn't be a part of the one that they would hang out in.
Yes. I mean, each one of these, so this modular system, it's going to require multiple launches of all the pieces, and then ultimately they all come together. But it's going to be an interesting proposition. Brian.
Curiosity, its mission is 2 years, correct?
Right.
And the nuclear reactor, what is the possibility of the actual system? You seem to over-engineer the predictive opportunity. What is the likelihood, the longest likelihood, that Curiosity could be working on Mars?
Okay, so first of all, Curiosity, it doesn't have a nuclear reactor on board. It's called a radioisotope thermoelectric generator. It's about 10 pounds of plutonium. The radioactive decay of the plutonium gives off a lot of heat. They use thermocouples to generate about 100 watts of power, and that charges batteries, and that's what drives it. So the primary mission of Curiosity is 1 Mars year or 2 Earth years. But that's sort of the same as the 90-day mission for Opportunity. That was its primary mission. They believe that the radioactive decay of the plutonium, I mean, that's physics as opposed to engineering, if you will, that should give them enough power for about a dozen years, maybe a year or 2 after that. And so that's sort of the likely cutoff time would be 12 to 15 years if all of the mechanisms continue working. But they certainly expect that it's going to have a longevity much beyond the 2-year primary mission. Okay. Well, I think we should call it a night. So thanks a lot, and we'll see you next month.